Have you ever just stared into a flame? A campfire, a candle, maybe just the burner on your stove? There's something totally mesmerizing about it. But behind that little flicker, there's a fascinating chemical story going on. It's a story all about carbon compounds and how they react with the air around us. All right, let's get into it. So it all kicks off with a really simple question, one you've probably wondered about yourself. How come some flames are so different from others? A gas stove, right? It burns with this clean, almost invisible blue flame. But then you light a candle and you get this bright yellow flame that leaves behind black soot. What is going on there? On one hand, we've got our clean blue flame, super efficient, super hot. And on the other, the sooty yellow flame. Yeah, it's bright, but it's messy. They're both fire, sure, but they're telling us two totally different chemical stories. And today, we're going to figure out the secrets behind this tale of two flames. Okay, the first secret is a process we all know, or at least we think we do, combustion. Put simply, it's just burning. But in chemistry, it's a super fast reaction between something, our fuel, and an oxidant, which is usually oxygen, that produces all that heat and light. And as you're got to see, the amount of oxygen you have, well, that's the main character in this whole story. So let's set the stage for our first scenario. We're starting with our fuel, in this case, a saturated hydrocarbon. Just think of it like the propane in your gas grill. Now, the absolutely crucial ingredient here is plenty of oxygen. We are giving this fire everything it could possibly want to burn perfectly. So we add a little bit of heat to kick things off, and the reaction is, well, it's flawless. Every single carbon atom from the fuel finds oxygen partners, and so do all the hydrogen atoms. The only things that come out the other end are invisible carbon dioxide gas and water vapor. That's it. No mess, no leftovers. And that is where our first flame comes from. This perfect, complete combustion lets go of a ton of energy as that clean, hot blue flame we see on a gas stove that's working right. It's pretty much the ideal chemical reaction for getting heat. But what happens if we mess with the recipe? Let's do the same reaction, but this time, we're going to be really stingy with the air. We're essentially going to starve the fire of oxygen, creating the perfect conditions for something called incomplete combustion. With not enough oxygen to go around, the whole reaction just gets chaotic. It's like a game of musical chairs where there aren't enough chairs. Not all the carbon atoms can find enough oxygen to become CO2. Instead, these tiny particles of pure, unburned carbon are created, and we have a name for that: soot. And here is where we solve the mystery. These tiny little soot particles get incredibly hot inside that flame, and they start to glow, just like the tiny wire in an old-school light bulb. And the color they glow? You guessed it, that familiar bright yellow. This is what makes a candle's flame so bright, but it's also what makes it so sooty. And here's the everyday proof you've probably seen. If the little air holes in your gas stove get clogged up with grease or food, they can't suck enough oxygen. The combustion becomes incomplete, the flame turns yellow and sooty, and you end up with a black-bottomed pot. So remember this, a black pot isn't just messy, it's a sign that you're wasting fuel. All right, so combustion is this wild, super fast version of adding oxygen. But we can also have oxidation happen in a much more controlled, deliberate way, adding oxygen to a compound without any fire at all. This is a whole different chemical ballgame. Just take a look here. We've got ethanol, yep, the kind of alcohol found in drinks, and with the help of an oxidizing agent, it gets converted into ethanoic acid, which is basically the main ingredient in vinegar. The key thing is how it gets transformed, by adding oxygen, but with no fire, no flame, just chemistry. So what exactly is an oxidizing agent? Well, think of it like a substance that carries around a bunch of spare oxygen atoms, and it's just really, really good at giving them away to other substances. A classic one you'd see in a lab is alkaline potassium permanganate. It's this really vibrant purple chemical that's fantastic at donating its oxygen. And what's really cool is that you can actually see this happening step by step. So first, you start with your clear ethanol. Second, you start adding that purple potassium permanganate solution. Third, as the agent reacts, it literally hands over its oxygen to the ethanol, changing it. And finally, here's the proof. As the agent gets all used up, its awesome purple color just vanishes. It's this fantastic visual clue telling you the reaction is done. Okay, so we've got fiery, chaotic combustion on one side and slow, controlled oxidation on the other. Why does knowing the difference even matter? Well, because these two reactions are happening all around us, all the time, powering our world and shaping our lives in some really fundamental ways. I mean, the gasoline in our cars and the natural gas heating our homes, that's all harnessing the explosive energy of combustion. Knowing about soot helps us understand why some fuels burn way dirtier than others. And it's a good reminder that a clean flame is an efficient one. We can even use this knowledge to our advantage. Ethanol, for example, can be a much cleaner fuel, because when it burns completely, all it makes is carbon dioxide and water.
So I'll leave you with this thought. We've seen that combustion is really just very, very fast oxidation. One is a roaring fire, the other can be a gentle chemical change. This idea of the same basic process just happening at different speeds is a really powerful one. So think about it. Where else do you see this? From the slow rusting of a piece of iron to the sudden explosion of fireworks, our world is just full of things that are, in their own way, burning at their own pace.